So, we were discussing about the AM detection using phase lock loop. AM detection, when we have what is called as synchronous detection, not the kind of detection that we are talking of, which is there in the conventional radio receiver, which is peak detection. Such a situation, we have the carrier that has to be produced exactly at the receiving end. If you can produce the carrier with the same amount of stability that the transmitter end has, then you can use synchronous detection for AM purposes. What is synchronous detection? Simply multiply the carrier with the AM and you get the detected output if you put a low pass filter. That is AM detection. Now, as far as the phase lock loop is concerned, this phase lock loop is used in order to extract the carrier, that is all, from the AM signal. So, what is done is AM input is supposed to go to the multiplier, the same AM input goes through a limiter, so that all the amplitude information is removed and the carrier frequency is applied to the phase detector. This is nothing but the PLL. Obviously, this produces the carrier at a phase shift of 90 degrees if it is originally tuned to the carrier, right. Now, if you use the phase shifted carrier itself for multiplication, you will not get an average, because if this is cos, this will be sine and average will not be there. Therefore, you have to additionally phase shift the so called generated carrier at this end by a further angle of 90 degree if possible. Even if it is 90 degree, it does not matter, there will be an average. Okay. So, another additional phase shifter has to be put here before you multiply using another phase detector. Okay. So, actually speaking, this is coming here as the second input. So, essentially you are generating the carrier, getting rid of the amplitude information here by putting a limiter, generating the carrier using a PLL and subjecting it to additional phase shift and then multiplying. That is what the phase. So, now this particular thing becomes a selective AM detection, because here you might get AM inputs of all varieties of this thing carriers, right, signal strengths, and what is selected is out of this the one that is tuned by the PLL to the specific carrier that you want to select, right. So, this is a selective circuit with AM being detected corresponding to the frequency to which PLL is tuned. Okay. So, this is a scheme for AM detection using PLL. The final application, and that also is one of the most important applications today in phase lock loop, is precision speed control. Almost all computer drives today are controlled with this kind of speed control scheme. Earlier it was voltage reference that was used for speed control, now it is frequency reference, and we have already seen how stable frequencies can be synthesized. Okay. So, from a given frequency reference, I can exactly synthesize to the same stability other frequency components. So, we can therefore, using frequency synthesis technique, obtain from a reference any frequency input. So, this is the reference frequency coming through frequency synthesized scheme, and that can be adjusted. So, this is applied to the phase detector, amplifier. Now, the low pass filter is nothing but the winding of the motor itself, control winding of the motor itself acts as a low pass filter. You do not have to specially put any low pass filter. So, this is applied through a power stage if necessary to drive the field winding of a motor. This is the other winding. These are the two control windings of a motor here. So, this is if it is given constant voltage here, right, this is going to be given the control voltage here. So, that the speed is controlled, speed and the direction can be controlled using this. Now, the speed of this motor is converted to frequency using what is called optical tacho. This optical tacho is like this. On the shaft of the motor, a dial like this is put with slots in the circumference which are equidistant. So, on this dial you cut slots which are equidistant on the circumference of the dial. Then you put what is called an optocoupler such that the light that is being emitted by the LED here is collected exactly by the light detector on the other side. These optocouplers are already available in this form with a slot. They can go right into the slot. The advantage is they have the hole here, so that the light emitted just exactly falls on the light detector. That is what is called an optocoupler. This kind of optocoupler suitable for this optical tacho generator is readily available in the market. Okay. So, you have to these discs also can be made by using what is called photolithography technique. So, that you have slots cut exactly equidistant and around the circumference. So, what happens as this rotate, the light will be cut off or permitted depending upon whether the slot is right in front of the beam or not, right. So, you will get an output here at this point, at the LED point. What kind of output you get? Almost looking like a sinusoid, because whenever it reaches exactly the slot center, there will be peak output. Okay. So, you will get a nice almost sinusoidal signal, right. This has to pass through Schmitt trigger. That means, what will it become? It will become a square wave of the same frequency. So, after it goes through Schmitt trigger, the whole thing now can be treated as nothing but voltage controlled oscillator, right. This voltage controlled oscillator is now designed not using electronic circuitry, but using a motor as part of the whole scheme, right. So, this voltage is now simply controlling the frequency of the output pulses. So, once this becomes an integral part of the PLL system, this VCO becomes an integral part of the PLL system. What is going to happen is just as what happened in our ordinary PLL, this frequency will be exactly same as the input frequency. So, irrespective of the load on the motor, the frequency is going to remain constant. That means, speed is going to remain constant. Okay. This kind of speed control is nowadays universally applied, okay, in almost all precision speed control schemes. And the, this frequency is going to be extracted once again from a crystal oscillator frequency coming through a frequency synthesis network, okay, which again will comprise of phase lock loops, multipliers, phase detectors and others. So, you can see that this whole scheme is very interesting, and this you can try out for any of your small motors, okay, is in the laboratory itself. There is no difficulty in trying out this kind of speed control schemes in laboratories. Now, these are the important applications of phase lock loop. There are lots of other applications which are minor. For example, phase lock loop by its very nature, okay, can modulate what? Phase itself, obviously. It is a subtle difference between frequency modulation and phase modulation. Even though they are linearly related, if you do phase modulation, you get a frequency modulated output. But only during the days of tubes, there were tubes which are directly doing phase modulation, okay, electron tubes. But after that, with the advent of transistors and all, the scheme for making available any direct phase modulation technique was not there until this phase lock loop came into picture. What can you do with it? We know that the phase lock loop has a phase shift of 90 degrees between its input and output if it is tuned, if the incoming frequency is omega naught q itself, okay, then the phase shift is 90 degrees. So, what you can therefore now do is here this is V naught q. You can superimpose over V naught q another DC voltage, okay, so that this VDC and V naught q, okay, together will determine the DC voltage of the VCO. Okay. So, this VDC is V modulating, right. So, what happens? V naught q will correspond to omega naught q, and let us say this is having omega naught q as the input. Then there is a phase shift of 90 degrees. Now, when Vm comes into picture, you are tuning the VCO to a different frequency compared to omega naught q. Okay. So, automatically the phase shift should change, frequency will remain the same. Okay. Now, the phase can be changed linearly by changing Vm. Okay. So, the output can be taken here, this will correspond to omega naught q, but okay, it is phase modulated. Obviously, this is also a frequency modulated waveform, it can be used, okay, because once you apply a DC here and vary the DC here, okay, of the VCO, you will get an FM. That is because phi is changing with respect to time. Is this clear? So, this particular scheme is directly modulating the phase of the structure. So, this is one such scheme which is there in as one of the applications of phase lock loop. This also can be used as an idea to generate a particular phase shift for a given. This can be a good phase shifting network. Okay. As far as the phase shift is concerned, for any particular specific frequency, you can obtain a desired phase by adjusting Vm. So, now we will start one of the most important blocks. I would categorize this block in that of analog circuits, because this is what is called D to A converter, okay, from digital switches and digitally word controlled switches, right. Digital word is the input to this, okay, and those switches which are controlled by digital word now responsible to activate the circuit and give you an analog output. So, let us see one of the important schemes of D to A converters. This is called weighted resistor scheme. As the name implies, we are adding, this op amp is used for summing up the currents. Okay. These are weighted currents, weighted according to the switch positions. Right. So, these switches are the control switches. These switches are controlled by the digital word, the input. Okay. So, when these are closed, obviously they pump in currents of the respective magnitude, which are binary weighted in this case, right. And therefore, we have an output V naught, which is clearly, let us write down V reference, okay, divided by R, and depending upon this, the coefficients here can take either 1 or 0. Okay. So, A3, let us say A3 is the coefficient which is operated by S3, which is going to take on 1 or 0. If S3 is closed, it is 1, otherwise it is 0. So, V reference by R plus V reference by 2R A2, V reference by 4R A1, V reference by 8R A0, in effect, okay, into minus R, or in a sense we have RF by R coming out, okay, RF by R coming out, okay, into Vref, and this is sigma. Okay. In fact, we can take out let us say 8R. Okay. So, what do you get here? A3 into 2 to the power, yeah, we will put it as AI 2 power I, okay. Is it correct? I equal to 0 to 3, right. So, this is an important thing. If therefore, this particular in any D to A converter, we have this for the analog expression. What is that? This is always coming out sigma, okay, AI 2 to the power I. Okay. This is the weighted scheme, and this corresponds to the analog output. These constants may vary depending upon the scheme of addition, right. It may be ratio of resistors or ratio of capacitors. If it is switched capacitor network, it will be ratio of capacitors, okay. And there will be always a voltage reference, okay. And therefore, what are the integral parts of D to A converter? Let us say one of the important block necessary to make D to A converter IC is the weighted scheme. It could be weighted resistor, weighted capacitor, anything. Okay. It is the one that determines the weights as given in this expression. So, the weighted resistor scheme here. So, it is important that these resistors have got to be precision, temperature independent, etc. Since the ratio is coming as resistor ratio here, it is the ratio that has to be temperature independent, okay, and the tolerance of this should be good. That means, if you want a precision D to A converter, you cannot normally go in for monolithic D to A converters. Have you understood this scheme? If you want very precision D to A converters, you have to go in for thin film, thick film components as resistors in this, okay, because we have seen that the resistors in monolithic form have very poor tolerance, okay, ratio tolerance, even though is better than absolute value tolerance, it is not acceptable, it is hardly, okay, something like 1 to 3%, right, which is not acceptable for precision converters. And you might have to go for maybe ratio of capacitors, which has a better temperature coefficient effect. That means, this weighted resistor scheme has to turn itself into weighted capacitor scheme. So, those will be switched capacitor networks, okay. And we have to have a precise V reference voltage. This we have also understood how to generate precise voltage references independent of supply voltage as well as temperature. Okay. So, this we have already seen. So, in a D to A converter, a voltage reference circuit is put, you have weighted resistor or weighted capacitor, okay, and the third important part is the switch. Which is controlled by the digital input, okay, word, and obviously its on resistance, off resistance, its stray capacitor, all these things matter as far as the accuracy and speed of operation of D2A converters are concerned. Okay. So, the switch is something that we have to learn about. This we have already learned. There is nothing to learn about these aspects. So, most important aspect is switching in D2A converters. Right. Now, this scheme of switching here, as you close this, the current flowing in this is V reference by R. Number 1, these currents keep on changing depending upon the current drawn from V reference will keep changing depending upon the position of the switch. Therefore, if this is not an ideal source, if it has a source resistance here, this voltage itself will change, right. So, that will appear as a noise, okay, which will be purely dependent upon the switch position. Okay. Have you understood this? So, this voltage will change, okay, in a very random fashion depending upon the switch position. So, that causes an error in this. This kind of error is primarily because you are drawing different currents from the same V reference depending upon the switch position, and V reference may have certain output resistance, however small. And obviously, the switch resistance also will come to picture. When it is closed, its on resistance will be adding on to R. This is another source of error in this, right. When it is off, it will still leak some current into R. Okay. So, the on resistance and off resistance of the switch, okay, is also going to contribute to the error in the output. So, we have to therefore see how these things can be improved. This scheme of switching is called voltage switch. Why is it called voltage switch? Because when the switch is closed, voltage across the switch is 0, but when the switch is open, the voltage across the switch is V reference itself. Okay. So, as matter regarding speed itself is concerned, since when the switch is open, it is a capacitor, until the capacitor is fully charged to V reference, we cannot take the output. That means, the speed of the D2A converter is going to be sort of limited by the fact that you are using a voltage switch here. Have you understood this point? The voltage across the switch is 0 or V reference. That means, the capacitor across the switch has to be charged up to V reference, right. So, before you take the output, therefore, there is going to be some limitation due to the nature of the switch itself. So, how do you get over this problem? This problem of the switch can be got over neatly by doing what is called current switching. What is that? Simply put the switch, this voltage will be constantly there, but then what is going to be done is location of the switch is changing. Right. Instead of single pole single throw switch, okay, we will use single pole double throw switch here. I mean, these are all not mechanical switches, these are electronic switches. Instead of one FET, we have to use 2 FETs, that is all. And now, the switch is either here or connected to ground. That means, the current V reference by R is all the time flowing into virtual ground or into actual ground. So, this is the scheme of things. So, this is what is called current switching, and it is this current switching which is now responsible for the increased speed. So, you can see here the subtle difference between location of the switch resulting in improved speed of operation. The price you are paying of obviously is in terms of number of switch electronic components. That does not matter in a IC. So, not only that, you would automatically notice that now the V reference is giving a constant current irrespective of the switch position, and therefore, even if there is some output impedance, it is going to be resulting in a constant error rather than a random changing time dependent error. Okay. This constant error can be easily compensated for, okay, whereas the random error which was earlier existing cannot be compensated. So, location of the switch here, making it double throw, okay, single pole, is going to work very well in resulting in a current switch. Now, the switches themselves could be simply MOS switches, right. One gets Q as its input, another then gets Q bar. Okay. So, you have MOS switch, or it could be even diode switches. Okay. So, for example, using diodes one can make a switch like this. Look at this arrangement. Right. If this voltage here is, let us say, negative, this is off. Right. The current will be flowing through this, right, forced to flow through this like this. If this voltage is raised to a higher level, positive, right, immediately you see that the current will be diverted onto this, and this is going to be off. Okay. So, by making these could be your digital output themselves directly, right. In the sense, you can therefore, I mean actually inverted part of digital. If you want the thing to exist, this will have to be low, okay, then it will exist, right. So, if your actual input is 1 0 1 1, say, then what you have to apply to this will be 0 1 0 0, right. So, inverted. So, this kind of switch can work very well as the switch for this weighted resistor scheme, or we can use MOSFETs instead of the diodes, that you know anyway, wherein like this. You can replace each of these by MOSFETs, getting Q and Q bar as the input, right, corresponding to the word. Yes, this is, let us say, S3, this will be S3 bar, like that, so on. It is another scheme for switching. Right. Now, I would like to normally avoid the switch resistance coming in series with the resistance, because this is again a random variation which is going to occur. Okay, it is going to cause serious problem. So, how do I really do current switching with switch not coming in series with the resistance, but switch coming in series with the current source. Okay. If you put the switch in series with the current source, then the switch resistance is not coming into picture. So, instead of this kind of scheme, what is therefore recommended is for avoiding the error due to the switch resistance, why not use a current source, let us say a transistor current source. Okay. And now you will put the resistance here, okay, and appropriately apply a voltage here, which is maybe V reference, okay, plus V gamma, so that V gamma is given. So, the voltage that you apply here is going to be V reference plus V gamma. Okay. Then the current in this is V reference by R. Now, you can introduce your switch at this point, either switching to virtual ground or actual ground. This scheme is what is normally adopted in most of the D to A converters ultimately. So, here it is avoiding what? The resistance of the switch coming in series with, okay, R, and the current ultimately is obtained by this current generator is going to be switched either to the virtual ground or to the ground. So, now you might say the same voltage is going to be applied through another. Now, there is a subtle difference here. The current here, if this is V reference by R, okay, the next current is going to be V reference divided by 2 R. It is an established fact that when the current in these transistors vary, the voltages will be different. So, if I have carefully adjusted this V gamma to be such that it is going to compensate for this transistor, then it will not do for this transistor. Is this clear? Because all these transistors are operating at different currents varying by a factor of 2. So, that is easily compensated for by making this particular thing. Okay, for example, this is V reference by 2 R. So, let us say I make another here. Okay. So, actual current here is V reference by 2 R. There are 2 emitters of this type. That means, this is going to give V reference by 2 R, the other one is going to give V reference by 2 R. In effect, okay, the V gamma of these transistors coming in parallel will be the same as that of V gamma of this, because all the transistors are operating at the same current. So, you make this area what? Twice that of this. Now, this has to be carried through, because the next one, if you are using the next one, right, okay, this is going to be again V reference by 4 R. That means, this has to be double that, this has to be 4 times that, right. We will stop at this stage, because it is just a routine thing here, V reference by 4 R. So, you can see a nice 3-bit converter, okay, using current sources which are being switched, and the areas adjusted accordingly, so that the compensation is exact. Okay. And this is the internal circuitry of most of your, I mean, this is done for 3-bit, you might have some 12-bit or 8-bit converters. You can see the circuit diagram given in the manual or something, it will exactly look like this. Okay. And basically, we have seen that it has a weighted resistor scheme and transistor current sources and switches and V reference. Okay. Now, this forms the essence of the internal circuitry of a D to A converter. There is a small difference here. There are two schemes of getting the required weights for the summation. One is the weighted resistor scheme, another is called R to R ladder scheme. It is an established fact that when you have 2R and 2R, the parallel combination here results in R. This R comes in series with this R, results in 2R, and that 2R comes in parallel with this 2R, so on and so forth. So, at any point here, if you look in through this, you will see an impedance which is always going to be R, right. So, the resultant effect, now if this is V reference by 2R current, this is going to be V reference by 2. Okay. This is going to be V reference by 2 to the power 2. So, at all these nodes you will get the so called weighted voltages necessary for summing up. Okay. So, at these nodes automatically. So, using these currents now by the same process of what? Switching either to the virtual ground or to the ground. So, this V reference takes always the same current here, okay, and the weighted resistor currents remain undisturbed, either they go into the ground or go into the virtual ground. You can get the same output that we have got from the weighted resistor scheme. The only thing is, for say 3 bits, here we need 3 plus 1 resistor, whereas here we need for 3 bits, for example, we double the resistors plus 1. Okay. Here you need n plus 1 for n bit D to A converter. Here you get 2n plus 1 as the output, so double. But the advantage here is the spread in resistance is only by a factor of 2 here, whereas it is going to be by the whole factor. Okay. So, either this scheme or that scheme is what is normally seen in your D to A converters. Okay. I think that should be sufficient for a discussion on D to A converter. In the next class tomorrow, we will just go into same scheme can be obtained by replacing these capacitors resistors by capacitors, right, and the switched capacitor networks. Okay. There of course, there is no question of current business, is the capacitor that is charged to a certain voltage using a switch, and then entire charge is transferred to the feedback or the output, okay, and that way you can bring in more number of capacitors at the input and pump in the current that is necessary to charge this feedback capacitor. Okay. So, this kind of switched capacitor networks we will discuss in the next class. Okay. Thank you.